simple surfaces or coordinate patches. Now, the general notion of a surface or a regular surface is essentially that we want to put coordinate patches together in a nice way, and surfaces will be the sets in R3 where we have done that. So formally, a subset M that's in R3 is going to be a surface when it is covered by what are called proper coordinate patches. I'll discuss proper in just a moment. But by covered, we just mean that for each point in the set, there is a coordinate patch that contains that point. And furthermore, if we take that coordinate patch, call it x, where p is in its image, then if we have some other coordinate patch y, then we want a nice sort of condition on the function y inverse composed with x. Okay, that condition, basically, we want it to guarantee that you get a coordinate transformation on those two charts. Okay, proper, what does proper mean here? It's a statement about the inverse of the patch being a continuous function from R3 to R2. There's some details involved there, some technical ones that let's not get into entirely, but importantly, this excludes certain subsets from being a surface. In particular, you can't have a surface that sort of bends back to itself and has a sort of T-like intersection of that surface bending back around towards a different part, getting near it, unless it's coming in a way where the tangent planes are going to line up. Okay, so our first example of a surface would be a sphere of any radius, say r naught. This is example 2.2 in your textbook. A sphere can be covered by 6 coordinate patches. I write down the form of 2 of those patches right there at the bottom. Okay, you can get the other 4 patches by just reordering the coordinates. For example, you could have what's currently the square root function that's in the third coordinate. That could be in the first coordinate, and then the y and z coordinate would be u1 comma u2. Alternatively, you could have the parameters be your first and third coordinate and the square root function in the middle. This gives you 6 patches. What you achieve by changing the coordinate direction in which the square root function is, if you just take 2 of these, then they have to be defined on open sets, and so that middle equatorial circle isn't covered by just 2, right? Because they're open sets, and so they don't have that boundary part that is at the z equals 0 plane, right? So you're missing part of the sphere, and you have to change the patches around in order to get all the points. You need 6 patches to do so. The cylinder is another example. I take a vertical cylinder here. This is example 2.3 in your book. You can do this with 2 coordinate patches, and both of them will have the form, or you can make both of them have the form cosine of u1, comma sine of u1, comma u2, where you restrict u1. Okay, so like for one of the coordinate patches, u1 could be strictly between 0 and 2 pi, and for the other coordinate patch, you could have it be strictly between negative pi and pi. When you just look at one of the coordinate patches, there's a vertical line on the cylinder that it misses, the vertical line where the x-coordinate is 1 and y-coordinate is 0. And that other coordinate patch catches that, covers it. The description I've given here doesn't restrict U2 at all, so this would actually be a cylinder that has infinite vertical height. In the book, it restricts it U2 to an open interval, which just changes the open set in the coordinate patch. So working with coordinate patches, it's helpful for the theory. It helps us to define and know what we mean by tangent spaces, but it can be a little bit impractical at times if you're trying to say things about the entire surface. So there's a theorem called the implicit function theorem that is more than what we have time to get into, but it's a wonderful theorem that really tells you a number of things. One of the things that it tells you is that it gives you a simple condition that is enough to know that a subset of R3 is in fact a surface. So if you have a set M, okay, and we're going to have that set be the set of points x, comma, y, comma, z, so that some function f is 0 at those points, where f is a differentiable function and has the property that its gradient is not the 0 vector at every point of the set M. So at every point where the original function is 0, the gradient is not 0. Okay. So if you have any set like this, then this makes a surface, a regular surface. A nice example is is a sphere. I picked radius 1 here, but any radius is fine. And so, for example, you can make that function f be x squared plus y squared plus z squared minus 1. The set of points where that's 0 is exactly the set of points on the radius 1 sphere centered at the origin. The cylinder that we discussed before is the 0 set of x squared plus y squared minus 1. There's a surface that we'll look at a fair bit. It's important for differential geometry, called the hyperboloid. You likely saw this in a Calculus 3 class when you were talking about paraboloids as well. These are both graphs of certain simple functions. The hyperboloid is the graph of x squared minus y squared. And so you can think of that as the 0 set of the 3-variable function z minus quantity x squared minus y squared. So that's another example of a surface. I'll explain the gradient condition in just a minute. Lastly, here's just something else. Some seemingly crazy surface, but really it's not a terrible function. But yeah, this ends up being a regular surface. And I'll leave you to explore that a little bit more. But let's just comment on the gradient of the first three. Okay, so the gradient of the function for the sphere there is just 2x, 2y, 2z. Now, of course, that is the 0 vector when you're at the origin, but the origin is not on the sphere. When you put in x, y, and z all equal to 0, then you don't get a value of 0 on that function for the sphere. Similarly, for the gradient of the function I gave for the cylinder, the only way to make it the 0 vector is to make both x and y be 0, and that would not be on the 0 set of that function. And the hyperboloid, just like the graph of any 2-variable function, it's going to have a gradient that is not 0 anywhere in all of R3. You see that third coordinate is just 1, and so that can never be the 0 vector. Okay, so at least for these first three, these satisfy the condition from the implicit function theorem, and so they are all regular surfaces. The surface that I labeled something else, I'll give you a chance to explore that yourself. Try taking the gradient of it and coming up with a reasoned explanation for why that gradient cannot be 0 if you are at a point where that function is 0.